Okay, in this video we're going to have a look at solving by separation of variables this heat problem. du dt is k d2 u dx squared with no flow boundary conditions and this initial condition here. So we are going to assume that we can find a solution which is a separated solution, something of the form u equal to x of x times t of t. And we're going to figure out x and t. So substituting that form of the solution into the PDE will give us xt prime equal to k times x prime prime t, which of course we've seen with our wave equation problem. We can separate by dividing by x and dividing by t to get all of the t's to the left, all of the x's to the right, and if that's the case then we must have that equal to some constant, which we're just going to name alpha in this case. Alpha is a constant. So given that, we can then separate that into two equations, the first an x differential equation with just x's, and then a t differential equation, t dash minus alpha kt equal to 0, as you can see there. Now for the boundary conditions that we've got, u sub x equal to 0, we can write them out again, du dx at 0 and t, that's going to be x prime at 0, t of t, and that's going to be equal to 0. Now we don't want a trivial solution because it won't satisfy the boundary condition, so we're going to set x dashed at 0 equal to 0, not t of t. The same thing occurs at the L boundary, x dashed of L and t of t, that's going to be equal to 0, so we're going to set x dash of L to be equal to 0. Okay, so given that, our set of ODEs expands a little bit. We've got the x equation is now going to have some boundary conditions. Still no conditions with the t equation though. So we've got x prime prime minus alpha x equal to 0 with 0 boundary condition derivatives. X dash at 0 and x dashed at L equal to 0. The t equation with no initial condition. We're going to leave that because it's non-homogeneous. We'll leave it till later and bring it in at the end. Now what about this alpha value? Remember we saw in the wave equation alpha could be negative, 0 or positive and lead to different situations. So there we've got it. When it's less than 0 we get a cos sine solution, linear when it's 0 and an exponential when it's greater than 0. And remember we've got those boundary conditions. So we're going to see what happens to each of these solutions with the boundary conditions one at a time. We're going to rule out some of them and keep others. So when alpha is 0, x dashed is a, and the first boundary condition implies that a must be equal to 0. But that automatically means that x prime at L will be 0 as well. So we don't use the other constant b, we don't get any information about it. We've automatically satisfied both boundary conditions by satisfying one. So that leaves us with a possible solution of x of x equal to that constant b. There's absolutely no reason to rule it out, so we're going to keep it as a potential solution here. X of x equal to a constant. And what about when alpha is greater than 0? Remember that was the exponential solution. The boundary conditions here, first implies a is equal to b, and the second then says that a is equal to 0. So b is 0, giving us x equal to 0 everywhere. And we don't want that because that will imply that u is 0, and that won't allow us to satisfy the initial condition, u equal to x. So we're going to ignore the case alpha greater than 0. Got two possibilities there. Alright, so for alpha less than 0, we're going to set alpha to be minus lambda squared, and then using the boundary conditions we see that b is 0, and that we need to choose lambda such that lambda is n pi over L. Gives us a cos solution, and so possible x of x solutions are that constant and cos solutions. Now remember the t equation, t dash minus alpha kt equals 0. We've still only got those two cases because we've ruled out alpha greater than 0. So looking at alpha equal to 0, t prime is equal to 0, and that's going to tell us that t of t is just a constant. That's the only possibility there. When alpha is less than 0, remember that we set alpha equal to minus lambda squared, and lambda is n pi over L. So we can substitute that in our t ODE, and we'll have t prime minus k n squared pi squared over L squared, and the minus becomes a plus, equal to 0. And we can basically just rearrange that and integrate to solve. It's a separable ODE, pretty easy one. And we should get something like t of t is equal to constant times e to the minus k n squared pi squared t over L squared. So e is my constant there. Alright, so we've solved our x equation and our t equation, and together that means we can form our possible solutions for the PDE. Remember, u is equal to x times t. So the possible solutions are, well, first of all, there's the constant case where x was a constant, which also had a constant for t, so we'll call it BD, b times d. Then the other solutions, alpha less than 0, ae times the exponential from the t equation, multiplied by the cosine from the x equation, and that's our other type of u's that will solve the original PDE. Any of those forms where n is we're going to take positive integers. But it turns out that the bigger exponential cos will reduce to the constant when n is equal to 0, so let's just put it all together and write it as a times the exponential times the cosine, and we'll state explicitly that n can be 0, 1, 2, 3, and so on. So that's our possible solutions. And remember, the initial condition was x, so we would need our solution that we've just found at 0 to be equal to x, and that would mean that we'd have a times the cosine, n by x over L. Now that is just not going to be equal to 2x. It can't be forced to be that way. It's impossible to satisfy using our separated solution. So what do? We go to our Fourier series. Remember that the PDE and the boundary conditions are homogeneous, so a superposition of separated solutions will also be a solution, and why not suggest a superposition which looks just like a Fourier series kind of thing. So a0 over 2 and an's in there, arbitrary constants. Now our initial condition will require x equal to a0 over 2 plus the infinite sum of an, exponential goes away at t equals to 0, it's just 1, and the cosine of n pi x over L. And just to remember, it was on 0 to L. And that's satisfied if we choose the an's as the coefficients of the Fourier cosine series, even extension of x over minus L to L periodically extended. So using our formulas, we've got an there, of course, given by 2 on L times the integral of x cos n pi x over L, the usual Fourier series formula here, which of course I'm going to leave to you to confirm by integrating by parts. We can find a0 is going to be L, and an is 2L times minus 1 to the n, take away 1, all over n squared pi squared. And that's for n greater than 0. So we can put that all together. So good idea to check your integration by parts there, or check mine more to the point. Putting those coefficients together, we can then form our infinite series solution for our PDE. So the formal solution then is given by u of xt is equal to constant L over 2, because a0 was L. It's infinite sum of the an, so that's the 2L square brackety deal, and that's all going to be multiplied by exponential from the t equation, e to the minus k n squared pi squared t over L squared, multiplied by the cosine from the x ODE n pi x over L. And that's our solution to our heat problem. All worked through separation of variables.